Welcome to Investigation 2.1, ladies and gentlemen. This is representing areas of rectangles. Our focus question for this particular investigation is, if the length n of a square is increased by 2 units and its width is decreased by 2 units, what two equivalent expressions represent the area of a new figure? So we're going to be doing more equation building, and we're going to be playing around with this a little bit. So let's begin. Major idea within this investigation is this concept of whether or not something is fair or a fair trade. So if someone were to give you 8 quarters, would that be fair enough trade for $2? And monetarily, we would say yes. The money-wise, yep, we're getting the same amount between the trade. But me personally, I wouldn't want a bunch of quarters hanging out in my pocket. I'd prefer the $2. So for me, that is not entirely a fair trade. So I want you guys to consider that with this next investigation. We're also looking at this idea. A developer has purchased all the land on a mall site except for one square lot. The lot measures 125 meters on each side, and in exchange for this lot, the developer offers its owner a lot for on another site. The plan for this lot is shown below. So the lot on the mall site is 125 by 125 meters. So if I were to do a little bit of math, the area of that lot is 15,625 meters squared. And it looks like, if I look at this, it's increasing by 50 meters on one side and decreasing by 50 meters on the other side. So we have 175 times 75. So you'd think that that would be a fair trade, right? You're gaining 50 meters on one side and you're losing 50 meters on the other side, but you still have the same meters perimeter on each side. But this particular lot has 13,125 meters squared of space. So really, is it a fair deal? I think we just answered that question a little bit with a big gigantic no. So playing around, sorry, my screen is being very weird. Playing around with this idea is what we're looking at for this investigation, whether or not something is fair. So here's our next little bit. Oh my goodness, I'm sorry. Making me sick. All right. Suppose you trade a square lot for a rectangular lot. The length of the rectangular lot is 3 meters greater than the side length of the square lot, and its width is 3 meters less. So if we were to look at this, here is my table. In this investigation, you will need to create your own table, and it's dealing with something where you're increasing by 2 meters instead of 3 meters and decreasing by 2 meters instead of 3 meters. But same sort of concepts, I feel like, are shown in these two tables. Here is one situation. So we have the original square lot. If we look at it, we have side lengths that are 3, 4, 5, 6, 7, and then a very generalized one of what if it was any length. Based on that information, we're able to create areas. So we have 3, if it's a square, we're going to say one side times itself or times the other side, which is squaring it. So 3 squared equals 9, 4 squared equals 16, 5 squared 25, and so on. And we end up with that very generalized equation and a funny little caret. So we end up with 2 raised to the second power, 2 squared. Our new rectangle, if you notice this, has increased in one length by 3 meters, and then the other one has decreased by 3 meters, making this first situation, if we had the original side length of a square being a 3 by 3, we end up with a length of 6 meters and absolutely 0 width. So 6 times 0 would be an area of 0. We have a straight line, so it's not a very good rectangle space. The next one, we have an increase of 3, so we have 7, and a decrease of 3, so 1. It's a 7 by 1 rectangle, and we get an area of 7. Same thing for 5, 6, and 7, and we end up with 16, 27, and 40, respectively. And the very last one is that generalized equation. So we have that side length that has increased by 3 and the side length that has decreased by 3. And in order to find the area of that situation, we do n plus 3 times n minus 3. So the very last bit of this table requires me to look at the difference in the areas. So looking at how the areas between the square versus the rectangle are different, or, oh, sorry, I just underlined the wrong thing for the square. Looking at the square versus the rectangle and seeing how they're different. So the area for one is 9 meters squared, and the area for the other is 0, so the difference is 9. If I look at the next one, we have 16 versus 7. Again, the difference is 9. 25 and 16, the difference is 9. It's 36. And 27, the difference was 9. 49 and 40, the difference is 9. So that, based on our table, is really an interesting pattern. The difference between one lot versus the other lot, even though you were trading the same amount per side, we were ending up in getting a difference of 9 meters squared. Or 9 meters squared. So the area of the square lot was larger by 9 meters than that of the rectangular lot. And one way to be sure of this is looking at this generalized equation. I already have here 9 squared minus n, but I want you to see how you can get that because you're going to be looking at it in Investigation 2.2. So we have n, I was saying 2 and I wrote a 2. We have n plus 3 times n minus 3. And we're going to be talking about this more in depth, but we can do a little bit of interesting math here. We have essentially two binomials, two numbers that are being added together, or multiplied together, or two numbers that are added that are then being multiplied together. And what we can do is use the distributive property, but take it to an extreme. So we can say, what if I had n and I multiplied it by another n? Well, I'd have n squared. Then from there, I also need to say, what if this n multiplied this negative 3? Because everything needs to multiply each other. So n times a negative 3 would get me a negative 3n. We can also look at this other side. We could say 3 times n, a positive 3 times n gets me a positive 3n. And then 3 times a negative 3 gets me a negative 9. From there, we can combine like terms. We have a negative 3 and a positive 3n. So that becomes 0, so our final result is n squared minus 9. Or if we look at our original equation up here, we get the exact same information. So we can see where that difference in 9 comes from. Essentially, we have our original square area, and we're subtracting 9 from it each time to get that rectangular area. So we can see that they're not going to be equal ever. This is our most generalized equation. The square area minus 9 gets me that difference between our square and that rectangle. Kind of cool that we can use quadratic equations to do this. So this little suggestion down here is, for each side length, can you tell if the areas of the new and original lots, or how the new and original lots compare? From which side lengths, if any, is the trade fair? And if we're looking at this, I'm not seeing any sort of fair trade. We are missing 9 meters every single time, even in the most general of situations. So if I had something that was 500 meters, for a square, 500 meters by 500 meters, and then I were to decrease one of the lengths and increase the other, so we'd have 503 to 497, it is going to be 9 meters smaller of an area than the original. When you're looking at something so big, maybe it's not going to mean so much, but if it's a smaller situation, it really could mean a lot. Take this situation, for instance. Smaller area, you end up with nothing if you were to trade it. So let's now look at our next question. We need to write an equation for the relationship between the side length n and the area A of the original A1 of the original square. So we need to write an equation for the relationship between the side length, n, and the area A1 for the original square. So if we're looking at the area for the original square, if we're going to find that area, we would take one of the side lengths and we'd square it because it's a square. Both the side lengths are the same. Now we also need to do the same thing for the next one. We need to write an equation for the relationship between the original side length of the square lot to the area A2 of the new rectangular lot. So we have A2, and we still have that original square that we're dealing with, but we're just going to be subtracting that 9. So it's going back to our work that we did up in the table. So we can see how the original lot compares to the new square lot. Next, this investigation requires us to sketch a graph of this information so we can really see what's going on. And it says, for the independent variable, show values from -10 to 10. So on my x-axis, that horizontal, I'm going to go from -10 to +10. And for our dependent variable, we're going to start at -10 and go to 30. So I'm going to do a little math magic and set up my graph. All right, so, sorry, I did a little jarring there. I just re-sketched the graphs. I put, for yellow, I put all of our squared values. So I took this information that is right in here. That's all yellow. And then for my red information, I took this information versus this information and sketched that. And so what we end up getting for this scenario is the following. Let's zoom in on it. Every time I see a squared number, like that perfect square, I was able to make a dot, and I was able to essentially create this sort of graph connecting these dots. So there is one of my graphs. This other one with the rectangles, I was able to create this graph connecting the dots. So looking at it, if I were just looking at our, say, this very first amount where n was equal to 3, my dot lies here, and this other one is 9 units up from it, just a little ways. So our dot shifted down those 9 units. Down, shift, 9 units, or 9 meters in this case. So looking at those two graphs, I'm seeing that shifting of everything down. So I can see that square perfect areas, those maximum areas that we could find, it's showing a parabola, but it's finding all those pristine situations. This other one, we're seeing the rectangular areas are just not cutting the mustard. They're just not as good. So which part of the graph makes sense for this situation? Well, they both do. If we look at the yellow graph and the red graph, we can see that the yellow graph and red graph are shifted. The yellow graph is the same as the red graph, but the red graph is just shifted down. And so the differences and similarities is we have like the same shape, and they are increasing similarly, but the second graph, they're different in the fact that the second graph has probably it has a different x-intercept and probably also a different y-intercept value. So those are all things that make a difference within this concept. So what I'd like you to do now is take this in, soak it in, have fun with it, and your job is to go through Investigation 2.1 and play around with this whole focus question now. We were just using the focus question of 3 units as being our defining factor, but now you're going to be looking at the focus question with 2 units. And are we going to see the same sort of change in area, or is their change in area going to be slightly different? So play around with investigation 2.1. Represent those areas of triangles. I should make this L a little bit bigger. And enjoy. I hope this makes sense, and I will talk to you guys on Monday. Bye.